Yeah, okay. So this is the last lecture in the Waveforms series. You're going to have a hands-on session, but before that, I think this is a nice transition because Eleanor is going to present the waveform modeling and probably talk about the different waveform models available out there so that you can segue into doing it yourself.
Yeah, okay, so this will be a sort of overview focusing primarily on the complete in-spiral merger ring-down models that we have available to us. Not really going to talk about the sort of fast Emery waveforms or the quasi-normal mode waveforms that are out there. So the modeling sources that these are largely applicable to are the massive black hole binaries and the IMRIs between the massive black hole binaries and the extreme mass ratio models. There's progress being made to extend these models into these higher mass ratio parts of parameter space. Definitely won't be reaching extreme mass ratio in spirals, or I would guess above about a mass ratio of 100. So okay, as a recap, you have seen this diagram now many, many times. We have, in the first previous lectures, gone over the three main sort of approaches that exactly resolve the space-time themselves. So there's the numerical relativity, applicable largely to comparable mass systems that are fairly close together, post-Newtonian or post-Minkowskian theory, applicable to systems of any mass ratio but that have to be at large separations, and the gravitational cell force for the large mass ratios for any separation. But if we want to be able to essentially cover the entire parameter space, we have to combine elements of all of these different approaches into a single model. And the two main models that have done this so far are the various effective one-body models and another approach, which is the phenomenological waveform models, which live in the phenom family. There's also a third approach, which is the surrogate models. These are sort of a second step, so they will be built either on top of making a surrogate of one of these effective one-body or phenom models, or straight from the numerical waveforms themselves. Okay, so when we are building up these models, we have to capture a whole range of physical phenomena. We have to be able to describe correctly systems that are non-spinning and align spin, and all our models need to be able to reduce correctly to that limit. We have to be able to describe systems with arbitrarily oriented spins. We have to be able to describe systems with asymmetric masses, systems on eccentric orbits, and eventually we have to be able to pull all of these components together and build models that are for fully generic binaries. And each of these different individual phenomena leave their own imprint on the waveform. So you can see here, for example, we have a plot of an eccentric binary and a quasi-circular binary, and the eccentric binary has this really, distinct pattern that modulates the amplitude. And then on the right-hand side, we have a plot of a processing binary. That is one where we have arbitrarily oriented spins, which creates this envelope which modulates the overall amplitude and also affects the phase and introduces these oscillations. Slightly, a bit of a mess. You then have oscillations being introduced by multiple different physical phenomena. You have to be able to capture these correctly. Asymmetric masses also make it much more important that we correctly capture the higher multipole content in the waveform signal. And for aligned spin systems, for example, you get the hang-up effect, where if the spins are aligned with the orbital angular momentum, and it takes a lot more time to radiate that away, these merge at a higher frequency. If they're anti-aligned, then you get a plunge much earlier on, and things merge at a lower frequency. So it's very important that we capture every one of these physical phenomena when we're making our waveform models. Okay, so the theoretical formalism that underpins a lot of these models is the effective one-body formalism. This is built upon the post-Newtonian work that Anna was discussing earlier in the week. Essentially, the post-Newtonian results give us this accurate description in the early in-spiral stage when the black holes are far apart, but it breaks down as they get closer together. We want, well, the motivation behind this formalism was to be able to extend this analytical description to later in the in-spiral, and ideally through merger and ring down. And this is done by employing resummation methods. So in the effective one-body formalism, you essentially do the same sort of thing that you do in Newtonian relativity, where you map the dynamics of a two-body system onto that of a test particle moving in the perturbed metric of a much larger body. So you have your center of mass frame, and then you need to be able to evaluate this external space-time around your center of mass for a small body. And this is done first for the conservative dynamics. So leaving aside the radiation reaction, you write this as a Hamiltonian, where we have an effective Hamiltonian of a test mass mu, which is moving in the Kerr space-time generated by a mass m, and this is deformed by the small mass mu by our deformation parameter mu. And then we have our Hamiltonian, and then once we have the Hamiltonian, we then introduce the radiation reaction. And in all of these cases, we are resumming the Pn equations. So this Hamiltonian here encapsulates all of the resummed terms of the Pn expansion for the conservative dynamics. And then when the radiation reaction is introduced later, this is also resummed, traditionally via Pade resummation, but more recently, sort of a whole range of techniques, slightly more advanced techniques have been used depending on your model and so. No question. That's the question. Okay. Great. So then, based upon most of the semi-analytic models here that I'll be describing do use this effective one-body formalism in some way to construct their model. There are two key families that it sort of underpins the entire approach. The first is the SEOB family, which uses, in the in-spiral, the effective one-body formalism just as it is. But it also, despite the fact that this formalism was designed in order to accurately capture the merger and the ring down, it was found that actually for the level of accuracy that we require for modern gravitational wave detections, this is not possible to achieve through this approach alone. And so you do need to be able to incorporate numerical relativity, information from numerical relativity in there. So firstly, for the late in-spiral, you add in essentially higher order terms for which you don't know the value of the term analytically, and you calibrate these higher order terms to your NR data, and you use that to push your theory to higher order approximation. Yes?
Sorry, just to understand the plot there. So, what's the? Like, I'm just trying to understand if why you use this SOB thing. So, is it much lighter computationally, or is it just completely different from NR, or is it based on NR? Sorry.
So okay. So the SEOB model is a complete IMR model. The NR waveform itself has to be started at some frequency and then evolve forward. So you don't get the entire in-spiral part. For this model, you use here the effective one-body formalism. You could use PN to just generate it to an arbitrarily low frequency.
So, like for example here, especially where you zoom in, like do you need to? It looks like you don't need NR, right? But even at the merger.
So NR has been used to calibrate that part. So this very early stage, that's not even on your plot, is pure analytic theory, effective one body. This late in-spiral stage, sorry, I can use this. This late in-spiral stage, you're still using the effective one body formalism, but you have these really high order terms which only contribute for the higher frequency part of the signal. And these higher order terms, you have taken your theoretical waveform, but left some free coefficients, taken your NR waveform, and worked out the value of those coefficients based on what the NR waveform looks like. And that has adjusted your theoretical model a little bit to account for the nonlinear relativistic dynamics that we have in the merger and ring down. Then when you get to the merger and ring down, really we actually find that the analytic formalism doesn't work at all. And so at that point, we just sometimes come up with a correct, the phenomenological expression. What does this look like? Oh, it looks like this. And then I calibrate it to NR, and I use that entirely. I will go through that in a lot more detail for an example later. But this is here. And then for the ring down, particularly the EOB models, they use results from perturbation theory, so the quasi-normal mode stuff that Marta was talking about yesterday. And that quasi-normal mode stuff can take over. So you only, this region will be probably almost pure NR information. This region, post-Newtonian effective one-body, and this region also analytic perturbation theory, black hole perturbation.
And SOB is there to like sew them in together.
And SEOB is one of the many ways that, yeah, we stitch everything together. And you can see nicely in this plot, one model, it doesn't matter what the name is, but the model in blue wasn't properly calibrated. It wasn't designed here. And so you get a dephasing. And I say properly, information was discovered later that you build upon. It wasn't they did it wrong. They just didn't know. And so you get some dephasing, but when you correctly account for everything and all of the physics, then you get this correct phase behavior. Yes?
The S stands for spin?
Yes.
Okay.
Yes, initially SEOB. EOB, they did it for non-spinning, and then SEOB, we've included spins. And then next I will talk about TEOB, where they included tides. But also the name has at this point become meaningless because now everybody does everything. So SEOB, as you can see here, also does tidal and generic spin interactions and generic orbit, so eccentric systems. And it is suitable for intermediate mass ratio in spirals and massive black hole binaries. And the bit where we are really confident and have tested this model is the massive black hole binaries, because this is one of the main models used by the LIGO-Virgo-Kagra collaboration. And so we really know for comparable mass ratio systems, this is fine. Once you start to push beyond the numerical calibrated part of the region for which the model is applicable, this part will still be totally fine because that's analytic and that performs as you'd expect, but the calibration will start to break down. And so extending this to proper IMRI systems will require work in the next few years. So, okay. Then we have the, oh, no. Yeah, the TEOB family. The TEOB family attempts to use less information from numerical relativity and more fancy analytical approaches. In general, as we'll discuss sort of at the end of the lecture, this probably means that for massive black hole binaries, it's a bit less accurate because it, this merger ring down part isn't calibrated fully to NR. But it might mean that it extends a bit better to higher mass ratios because it's a sort of overall analytic approach that can be carried on a bit better. Yes.
I don't need to think. I just wanted to make sure I knew what you meant by higher mass ratio because I've seen different standards.
Okay, so yes, I think of anything above about 10 to be a higher mass ratio.
It's the big one over the small one.
Yes, I also think about it that way around.
Okay.
Yeah. Yeah, but that is because largely I work with comparable mass systems, unlike so yes, so this version of the model can be extended potentially more easily to these higher mass ratio systems, and this work has already started doing this, where they've been incorporating information from gravitational self-force to make this more reliable for these higher mass ratios. Cool. So then the other family of models is the phenomenological models. These are also a complete in-spiral merger ring-down model. They evaluate down to arbitrary frequencies. Unlike the EOB approach, where, yes, you have this analytic formalism, but it does require the solving of integrals in order to come up with your waveform. So you start with the dynamics of the system, and then you solve these integrals, and you get out your waveform. So they are not slow. They are not fast. These models largely use closed-form expressions, which make them a lot more efficient. And particularly, these models can be generated in both the time and the frequency domain, but the models in the frequency domain are very, very computationally efficient. They use a similar sort yeah?
Well, you just said that the effective one-body is also analytic, so why there is no closed-form expressions?
As in?
Like here you said that phenomenological models have closed-form expressions, so they are efficient. Mm-hmm. But in EOB, you were saying that there's like kind of analytical potentials that will resound, something like that. So I would imagine that they are also closed-form expressions. But it's not the case, or, I mean, what's the catch that I missed here?
So, okay. I mean, as I will go on, you will find that we do, both models use some things that are closed form and some things that are not closed form, so the details get a bit blurry. My understanding of the effective one-body formalism is that you get the expressions for the momentum, you know, you get the equations of motion. Those you have solved analytically. But you have to go from the equations of motion to the waveform. And it is analytic, but it is not closed form. Whereas for PN, you use post-Newtonian theory in the early in-spiral, and for post-Newtonian theory, you have ready-to-use waveform expressions, and you just code these up, and then you stitch these onto a phenomenological ansatz, and the whole thing is closed form. Okay. Is the principle, the basis on which these models were built. Okay, so they are also constructed via a piecewise ansatz. So similarly, we have PN at the in-spiral start, then we move in the merger ring down, we just have this phenomenological ansatz which describes what our data looks like. And then in the intermediate region, you connect this smoothly. The two pieces are stitched together using a variety of different methods. And essentially in this merger ring down region, in the blue region, you look at the shape of the waveform. Here, the post-Newtonian, the effective one-body, everything has broken down. It does not describe what the waveform looks like here. And so you say, what does that look like to me? And it looks like a Lorentzian upside down. And so we describe it as a Lorentzian. And then we calibrate the values of the coefficients of the Lorentzian. And then once we have done that, we use a data set of numerical waveforms, and then we work out what the fit of the waveforms is across the parameter space. And that tells you you can then generate a waveform at any point in the parameter space. Yes?
You'll cover it next, but so can we compare the two approach? Is there one that does better than the other? Because there seems to be both suitable for the same sort of, I mean, they seem to be both suitable for, like, I don't know, massive,
So both waveforms, both waveforms attempt to describe basically the same kind of systems. This is very useful early on, because if your two waveforms look the same, I mean, it's still something that we use today. But yes, you can compare the approaches from a practical standpoint, you can compare them in terms of computational efficiency. You can compare them in terms of accuracy across the parameter space. And at the very end, I have a comparison of lots of different models. I personally don't think you can compare them in a way that says this one model is better than the other one always. So, okay. Yes.
You said something about frequency and time domain of these models, and you said that one of them is more efficient. Can you say again which one and why, if you can give us an idea?
Okay, so again, this is slightly from a LIGO perspective, I think, this statement. It depends how the Lisa data analysis goes. From a LIGO perspective, we do the data analysis directly in the frequency domain. So any time domain model has to first be Fourier transformed, and then you can do your data analysis. Whereas if you create your model in the frequency domain, you get rid of that Fourier transform. It's instantly much faster to evaluate. In the EOB, the effective one bodily formalism, is developed in the time domain. You can only develop those models in the time domain. You have to have a Fourier transform. With the phenom family, you have post-Newtonian expressions that are in the frequency domain. You can use those in the in-spiral, and then since you're just coming up with an ansatz, it doesn't matter whether you're in the frequency or time domain. So these frequency domain models are faster and can be included in the phenom approach. There is also a time domain model part of the phenom approach. This is still faster than the EOB models because it uses these closed form expressions rather than having to go from the equations of motion to the waveform. And so it's more computationally efficient anyway. Okay. So those are the set of semi-analytic models that are the primary models that we use for analysis. Then we also have these surrogate models. These are based on a data-driven approach and interpolate these data sets without really caring what the waveform looks like underneath. So you can make a surrogate model of any data set. You can make a surrogate model of by generating an EOB model across the parameter space and then interpolating between it, or a phenom model, or a set of NR waveforms. The advantage of making a surrogate model of one of your semi-analytic models is it will be much faster to evaluate. And so sometimes we do that to speed up the other models. But the real use of the surrogate models where they come into their own is these NR surrogate models where you sample, you generate a huge number of NR waveforms and then interpolate between them. And these make extremely accurate models. So they are generally typically about an order of magnitude accurate than the semi-analytical models we have available to us. But they are limited, and they are limited because they can only be as long as the length of the NR simulations you've built them from, which means that given, for LIGO, if I start my data analysis at 20 hertz, then I cannot use my surrogate model for any binary with a total mass below 60, which means you actually can't use it for any system that has a parameter distribution that might extend below 60. You have to have that excluded below your 90% confidence. For LIGO, this is okay. This is, a third of our sources we can still use it for or something. For Lisa, this is obviously a huge problem. There are, again, ongoing developments in this field where you hybridize, so you stitch together a post-Newtonian waveform and a surrogate waveform on the fly, and you're therefore able to generate sort of surrogate waveforms in the merger ring down using analytic theory in the in-spiral for arbitrary length. But it's not yet known how accurate these will be compared to the pure NR surrogate models because, for example, you have to have the analytic theory available, which limits you in the modes that you can include in your model. And the hybridization will come with its own error budget. And so basically we wait to see. The other major drawback in the construction of these models is that because you have to really densely populate the parameter space with your NR waveforms, they are limited in the parameter space that they can cover, and extending the model beyond where it lies is extremely complicated. So I think the latest greatest surrogate covers the full processing generic spin parameter space, but only goes up to mass ratio 4. And that has been the situation for, I think, the last 6 years. We keep being told any day now we're getting the one that goes up to mass ratio 8. But in order to extend that model beyond that, it might take another 5 years. You know, it's slow. Whereas with the semi-analytic models, the number of numerical waveforms you need to construct them is much smaller. So model development can occur on a much faster time scale. And the hope of reaching, say, in-ring waveforms is more realistic. However, there is this surrogate model constructed which uses a combination of numerical waveforms in the comparable mass limit and waveforms calculated using black hole perturbation theory in the, I say extreme mass ratio limit, definitely in intermediate mass ratio limit. I think it goes up to a mass ratio of 10 to the 4. So that is there. Unfortunately, it's a bit difficult to judge the accuracy of that because we have the waveforms it was built from, but we don't have anything else to compare and contrast it against. Okay. So those are the main families of the models and the principles behind the models that I will be discussing here. What are the requirements on these models to have them suitable for use in data analysis? Ideally, obviously, they would be infinitely accurate, they would be extremely computationally efficient, everything would just work wonderfully. This is not realistic. We're quite frankly not going to achieve it. But we do need to have highly precise, highly accurate waveform models because any error in our model can propagate forwards. It can make it difficult to detect the signal if the error is too large and it's simply not correctly modeling the source. It might make it very difficult to estimate the parameters and the properties of the source that you're seeing. Further down the line, it will affect any inference you want to make on your detections, whether that's mimicking deviations from GR, when actually it's just that we don't fully understand the effect of some eccentricity on the orbit, whether it's an attempt to make estimates for the rate and rate of black hole mergers and population of these things in the galaxy, which feeds into formation models, understanding where did everything come from. And specifically for LISA, where you'll have this overlapping signals, if your model is insufficiently accurate, when you try to subtract it from the data set, you'll be left with all these residuals, which will mess up the inference with everything else. So the most important thing that I will focus on here is going to be the accuracy measures, leaving aside the computational efficiency for now. We can look directly at the waveform. We can consider things like dephasing. We can look at errors in the fits. Generally, when we're considering a data analysis perspective, we use this quantity called the match. And so this is essentially the noise-weighted inner product between two waveforms. And then you optimize it over a number of parameters. And the parameters that you optimize it over depends on the system that you're considering. So for a simple line spin model that consists of only the dominant quadrupole mode, you just align it over time shifts and phase shifts. So it doesn't matter where in time your signal is occurring, and it doesn't matter whether, where in the binary you are. That's an equivalent system. Once you start to include higher modes in this system, the phase now has a meaning, but the polarization of your source doesn't. So now we optimize over the polarization instead. When we consider spinning systems, we might optimize over things like the in-plane spin angle, where again, this doesn't necessarily affect the waveform signal. When we create models at the moment, we don't include a measure of how accurate they are and where in parameter space they're most accurate. But it's one of the things that we really need to do going forwards, is that every model should come with some kind of error bar associated that can feed into the parameter estimation. So we have an accurate idea of, For this system, my error bar from my modeling error is tiny, but for this system, it's right on the edge of the parameter space where I'm confident, and therefore the error bar is really quite large. And then once we have an understanding of the accuracy measure of our waveform, we have to understand how this relates to parameter space bias at all. So just because we know the accuracy measure doesn't mean that we know that it will be biased.
Yeah. So when you talk about accuracy,
Yeah.
what you compare your favorite waveform against?
So typically, we might compare it against numerical relativity
NR.
signals. This works for like the massive black hole binaries. Often we will compare the semi-analytic models to the NR surrogate model because it's an order of magnitude more accurate. We can use that as a proxy. Once we get outside the region in which we have reasonable NR, we have to just compare the models to each other. And we then can't say which one is better, but we can at least say, okay, they agree, we're confident, oh, they're really starting to look different. One is wrong and probably both. Okay. So there are many attempts ongoing to work out how we understand the bias that we're likely to see in our waveforms. And one of the key ways that we do this is by using something called the distinguishability criterion, of which there are also many different forms and many different interpretations of how to use this. So I am going to write the most simple one on the blackboard and then talk through it, but this is not necessarily the one that people like to use now. So, okay. Okay, so this says that in order to be able to distinguish between two waveforms above the modeling error, your mismatch must be your match must be greater than 1 minus the chi-squared probability density over 2 times the SNR squared. And this chi-squared depends on your confidence interval and the dimension of your parameter space. And so, for example, we could say, I want to know for 90% confidence, will this be within my error bar? And then I'd say the biggest contention is how does the parameter space feed into this? Because when we're talking about something like a fully generic binary, right, we have 2 mass parameters, we have 6 spin parameters, we have 2 eccentric parameters. So we're getting up to maybe a 10-dimensional parameter space. But when we look at the parameter estimation, when we report the values and the errors on our numbers, we report them one number at a time. So that error bar, is it for the full 10-dimensional parameter space, or is it for the one number that you are thinking of? So here, for example, in this plot, this is a 2-dimensional parameter space. The model might have been run on a higher dimensional parameter space, but we're looking at the projection onto the 2D parameter space. And so this plot, we're saying the black dot, that's the true source parameters. The center of the ellipse is obviously what you would report as your value, and then the error bar given by this. And you can see that the black dot, there's some bias in there coming from a waveform mismodeling, and it is just inside the SNR 60 line, well inside the 50 and well outside the 250. And so this black dot SNR 60 here is the SNR that this formula would tell you for 2 dimensions. This will be right on the boundary. So from this, it would imply that, okay, this is a reasonable approximation. But this is sort of proof of concept approach and really needs to be extended to higher dimensions and test that everything is working. But the other sort of annoying thing that comes in here is that we cannot say that it will be biased, only that it might be biased. If your model fails this criterion, you have a possibility of your parameter estimation being biased. It could still be perfectly right. But if you're well under the threshold, I am confident in my model. If I am well over the threshold, I am very worried about my model. If I am close to the threshold, we're uncertain. But saying exactly what's going on there is a bit of a mess.
Eleanor,
Yes.
did I understand correctly the idea behind this is that you require that the potential bias due to mismodeling is below the statistical fluctuations or uncertainty that you would get from your inference?
Yes. Yes. Essentially, yes, I require, sorry, not a data analyst, so maybe saying exactly the same thing in a slightly different way. If this is my posterior and this is my 90% confidence interval, I require that my true parameter be within this confidence interval to within, if this is 90%, then it has to lie within this to within 90%.
The one that you get from your model.
Yes.
Yeah.
And if
Potentially mismodeled.
yes, and if it fails this criterion,
It might
again,
be
we
outside.
don't know that it isn't, but it might not be. And yeah, essentially this is trying to say, what is the value of the mismatch where we might start to see errors? And if we then want to be able to use this to work backwards to say, okay, for all sources, we want to be confident to 90%. If I run a mismatch analysis, which is much more computationally feasible than running a full parameter estimation study with hundreds of different injections, can I say, okay, in this part of the parameter space, we're well within this threshold, therefore we can trust the model. In this part of the parameter space, we're not. Don't use it here. Or if you use it here, caution.
The mismatch is between two waveforms, am I right?
Mm-hmm.
Okay. So what are these two waveforms in this case? If I'm not sure if I get it right. One is the true one,
Yes.
and the other one?
So
is
you compute your mismatch. For example, if we compute the mismatch between a numerical relativity waveform and a phenom waveform,
Okay.
and we say the numerical relativity waveform is more accurate, so we use that as our true source, and we inject the numerical relativity waveform and perform our parameter estimation with the phenom waveform. How does the mismatch between those two waveforms relate to the bias in the recovery?
Okay. Okay. So you have a benchmark, kind of, like
Yeah.
you are
Yeah.
based on numerical relativity.
Yes, normally numerical relativity, but for systems where we don't have numerical relativity, we might use something else as a proxy. If we were particularly interested in in-spiral waveforms for high mass ratios, we might compare your model with an Emery waveform, for example, and say the Emery was a fast Emery waveform.
I always get a bit scared when I see chi-square. But, okay, so when there's a chi-square, there's an assumption made of Gaussian noise. Basically, you're assuming that your posteriors are going to be Gaussian because, like a Fisher posterior is what you would expect. Okay, so that means that this would be valid at high SNR conditions. Okay, cool. If I was to look at it in terms of I know you say you don't do data analysis, but like in a PP plot, right? Would this mean that we are overconfident at higher values of nominal coverage? I'm trying to see how I understand a PP plot better than than this perhaps. So I'm trying to, can I map it back to PP plots and try to think of it in that direction, or do you already have an intuition in that direction?
I don't know. We do produce PP plots when we produce our waveforms, but we normally do them where we inject the waveform and recover with the same waveform.
Yeah, there's no model misspecification in that case.
Yes.
Okay.
In this case, we want to think, what is the mismatch? What is the error if we inject a different waveform to the one we're recovering with? And then, yes, I guess the PP plot would work as well. You'd say, if I inject always with the true signal and recover with my model, do I go outside those thresholds?
I think that's what I'm asking, maybe.
Yeah.
You want to
Okay, so maybe you're going to talk about this later, but as I understand, this is a measurement of bias that you would get if your source was completely isolated, like in a kind of LIGO-Virgo situation, and you're doing parameter estimation on it. In the Lisa case, the bias I worry the most about is confusion for other sources. So you analyze with one waveform, you leave a residual, and that gets confused for something else. Is this being measured also?
Yes, that's also something that people are looking into. I'm not sure that it's something that we worry about from the waveform modeling perspective so much. We want our models to be accurate for the source that they are describing. If your model is fully accurate, then when you subtract it, you will leave behind a smaller residual. If, though, you've somehow had an overlapping signal or something, that means you've misidentified the source. This is really a data analysis problem.
What I mean is maybe you get high overlaps and then you get confident in your waveform model, but still the residuals are big if you're not measuring them. No?
I'm not sure why, if you have accurately recovered your parameters, you're going to leave behind large residuals.
But, I mean, another way to think of this is like, let's say you haven't fit all your like a GBs, right? And so the assumption is that the noise is so outside of the source, you just have the noise, and that noise is a Gaussian noise. If that assumption fails, as would be the case if you have some other source there, that would mean your likelihood is no longer Gaussian, I guess, and then this whole thing, then chi-square is not a valid assumption, right? Or something along those lines, maybe.
Sure.
Maybe I'm saying something stupid. Right?
I don't know. Maybe you have a super high SNR massive black hole binary. You get a very good match on the waveform, very good overlap, but still you leave a residual that is, compared to that, is small, but then it's still big enough that it might get confused with something else. Oh, so that's why you're scaling with SNR.
Yeah.
Okay.
Okay.
A lot of interest.
Yeah. Okay. Oh, sorry, I've lost the thing. Okay, so now, having covered all the sort of ideas behind how we build the models, how we test their accuracy, I'm going to go through a case study for creating a phenomenological processing model. And I should caveat here that the reason I have chosen this example is because it is what I work on. It is not because it is any particular, relevant source, but I can talk about it in some detail. So, I've talked about processing systems a lot, but just in case anyone is unfamiliar with the concept, a processing binary is one where the spin on one or both of the black holes is misaligned with the orbital angular momentum. Therefore, it couples together, and it causes the orbital plane to process. And this processing of the orbital plane over time introduces oscillations in the amplitude and phase of the waveform, which make it extremely hard to model. Particularly if you think about how I was talking about we model systems where we come up with this nice, neat phenomenological ansatz. It's really not possible to have a phenomenological ansatz of something that looks like this. So we have to have a way of making the system simpler. And when we model processing systems, what we actually do is track the optimal emission direction. Right, so when you have an aligned spin binary, well, if you have any binary, the majority of the power is emitted perpendicular to the orbital plane. For an aligned spin binary, you set up your coordinate system so that you're decomposing your spherical harmonics so that this perpendicular to the orbital plane, you have the 2-2 mode, and therefore most of the power lies in the 2-2 mode. And now my coordinate system doesn't change with time, and so I just have this nice system where all the power is being emitted in the 2-2 mode, pretty much. When we have a processing binary, what we do is we actually just track the you can track one of two things. Most sort of correctly, you would track the direction of which the optimal emission direction, so the direction in which most power is emitted. You can also, for example, track just the direction that is perpendicular to the plane of the binary. For example, if you're using post-Newtonian theory, you have an expression for the orbital angular momentum. This is approximately perpendicular to the plane of the binary. These two directions are not exactly the same, but they do the same, they serve the same purpose when we're modeling. Now we transform into this frame where now all of the power, the majority of the power, is once again being emitted along the z direction, and therefore when we put the waveform in this frame, we get a nice clean waveform where again the 2-2 and the 2-2 multipoles are dominant. Most of the power is there. The other multipoles are now subdominant, and we can go back to modeling this like an aligned spin binary. And in fact, we get a very, very nice mapping where this waveform essentially is the waveform that we see for a comparable aligned spin binary, except that we have to take account of the in-plane precessioning spin when we work out the final spin once the two black holes have merged and adjust this ring-down component. However, we then also have to come up with a model for the transformation that we've done. So we split our model into two different things. One, the sort of underlying aligned spin binary, and two, the transformation. And this takes the form of three angles, Euler angles, that you would use to transform between any frame. We have alpha, the rotation around the inertial frame z-axis, beta, the angle between the optimum emission direction v and the total orbital angular momentum, which we take as our z because this is approximately conserved throughout the evolution of the binary. And then we have the final angle gamma, which we can calculate numerically using the two. And this gamma essentially ensures that we do not introduce any sort of phase drift when we're performing our rotation. So it ensures that the phases are consistent between frames. So okay, now we've split our model into two components. We first have to model the coprocessing waveform. As I was talking about earlier, this is the phase derivative of an aligned spin binary waveform, and we have this nice sort of Lorentzian, upside down Lorentzian, in the merger ring down. This over here we would have our post-Newtonian expression, and now we have to come up with an ansatz that describes this. And essentially what we do is we can take intuition from both the post-Newtonian part, where it's a power series in f to the power, and so we have some of those terms, f to the power something, and then we have a Lorentzian at the end. And we can see that this Lorentzian, we know that it's centered on the ring-down frequency of the system, so that's nice and neat. And then we calibrate the coefficients of both the Lorentzian and the terms in power of f and come up with an ansatz for the whole thing. Then when we want to join it together, you can do a couple of different things. Sometimes we just come up with some sort of intermediate region, require that it's C1 continuous at both ends, and have some sort of simple functional form in the middle. The fancy way to do it is using collocation points, where you, instead of sort of just matching the ends, you have to match the value at each of the co-location points in the derivative and so on. Okay. The model that we base it upon is for nom-XAS. The model names don't really matter. I've written them here for completeness. It was calibrated to hybrid waveforms based on an effective one-body waveform, just the sort of theoretical waveform, really, for the in-spiral, and then NR in the merger ring down, so that you're able to calibrate over a larger frequency range than simply calibrating to numerical relativity would give you. And then when you make your waveform, you have post-Newtonian, and you do add, as with the effective one-body models, there are these pseudo-PN terms that also get calibrated to the data to improve that late in-spiral section. Then we add on a phenomenological merger ring down and connect the two together. However, that was a purely aligned spin waveform. Now we have to account for the fact that this is a processing binary, and we do have to make some tweaks in the even in the co-processing frame. And so you do a further calibration just as deviation parameters. So you have your overall aligned spin waveform, and then you just say, OK, and as a function of the in-plane spin, how much does this deviate from what the aligned spin waveform looks like? Yeah, you can see here that it's a very small shift between the NR and the calibrated waveform. We also found when we were developing this that there were a couple of other features of precession that people hadn't identified before, which needed to be taken into account. One is called the multipole asymmetry. This is essentially when you have an aligned spin binary, your plus m and minus m modes are symmetric. When you have a processing binary, this symmetry is broken, and they now oscillate about each other. And so, again, as before, this complicates everything. So what we basically do is average through it, model the system with the asymmetry removed, and then make a separate model for the asymmetry. So you can see that as we include more and more physical effects in our model, we do it by building up each physical component, one at a time, and adding them all in there to make the full complete model. The other feature that we identified is the effective ring down frequency, which I will come to in a few slides to describe in a bit more detail. Okay, now we've modeled our co-processing waveform, we need to model our precession dynamics. These are done in essentially the same way that we model the co-processing waveform. We use post-Newtonian expressions in the in-spiral. We use a phenomenological description in the merger and ring down. This is calibrated to a set of numerical waveforms. We can use a variety of different prescriptions for the post-Newtonian part. This is where I said actually things start to get complicated, because there are a set of closed form expressions which describe these angles. They are not as accurate as if you evolve the PN expressions themselves, and this accuracy has found to be important to capture the correct sort of phasing of the precession terms. So now the phenom models, some of them use a sort of evolution in some parts, and this slows everything down just a little bit. Nifty numerical techniques mean it's still not that slow. So okay, again, as before, we want to be able to capture, what have we learned when we do this? And we can see, for example, if you look at the blue line here, that's what your post-Newtonian prescription predicts for this system as you go through merger and ring down. And the black line, that is what actually happens. And they do not look at all the same whatsoever. And they shouldn't, because post-Newtonian theory doesn't describe merger and ring down. But essentially, you can't describe this analytically. We don't know a way to do it. And so you have to be able to use these sort of phenomenological descriptions and understand, what does that tell me about my processing system? What have I learned about the physics of these systems from the fact that this is what the various components look like when I look at my numerical data. Okay, so the first of these is the fact that this angle beta, remember the angle that describes our precession cone, it describes the amount of precession that we have in the system. It drops rapidly during merger. This part is post-Newtonian theory. This part even, you can come from perturbation theory. But this part right in the middle, we don't know. That's the merger, that's highly nonlinear. We just describe it purely phenomenologically. But what does it tell us? For example, you can see here that this has not dropped to 0. So I have my precessing binary with my spins going, everywhere. And then they've merged together to make a single binary, but I still have a precession cone. I have a single black hole, which is still precessing. Essentially, remember I was talking about this dominant emission direction. This dominant emission direction is not along my z-axis. It is still going round and round, and slowly may be decaying to 0. So it's slowly radiating away that perturbation. But that perturbation is not aligned with our z-axis. It's still off at an angle. Yes?
You said you don't really know, right? You can calibrate the NR.
Yeah, this here is an NR waveform. There's no model actually shown on this slide. But yeah, the model, so like on the previous slide, this is just from calibration to NR.
Okay.
There's no theory that has come in there.
And we have a follow-up.
Yes.
Where is the analytic estimate? Is that like an empirical or phonological estimate?
So that comes from black hole perturbation
okay,
theory.
so that's the...
And if you are familiar with black hole perturbation theory, you will know that these things decay. They're a complex, as Marta was saying yesterday, it's a complex frequency, and one of these gives an exponential decay. And so we do see the exponential decay. Maybe we've already reached the limit of our noise floor in our numerical simulations. You can see that it's decaying. You could also say that was flat, But okay, the exponential decay is in there, but the rate of that drop is not given by perturbation.
So that explains, I guess, why the NR is so different from this
Yes.
solid black line.
So that this analytic estimate is purely for the ring down.
Yeah, it's only valid after the...
Sorry. Ooh. The analytic estimate is given by the blue line here for the in-spiral. But actually, there's a huge region where neither really work. I mean, it's doing... This is an example that makes my point, right? Some cases the PN is a bit better than others. But never is this drop properly described at the correct frequency by the correct amount with the correct flattening off. Okay, so that's one thing that we learned from the collapse of this angle through merger. The second is that this angle is related to the ratio of the multipoles, of the dominant and subdominant multipole. Because when we're transforming from one frame to another, right, those waveforms, if you remember at the beginning, all the power is being spread out between the different modes. And so now power from the 2-2 mode in the co-processing frame is being shared between the 2-2 and the 2-1 in the inertial frame. And the amount by which this happens is given by our angle beta. And so if you do not correctly capture this drop, then you will find that, see in the NR, in the black lines, the frequency at which the multipoles start to fall off changes. Essentially, as it starts to drop, the amount of power in the 2-1 relative to the 2-2 fades. So the 2-1 turns over at an earlier frequency. This is sort of where the drop starts, and here where the 2-2 starts to drop and they go back to being sort of parallel, that's where the drop ends. If you don't capture that turnover correctly, then everything starts to fall off, the power falls off at the same frequency, and you don't get this hierarchy. Okay. So now, what does it mean for the final part of our system that it is still processing while it is ringing down. A quick recap from what Marta was talking about yesterday. Okay, we have our two black holes. They merge. They form a single black hole, which is a perturbed Kerr black hole. It emits gravitational waves at characteristic frequencies, known as quasi-normal modes. The frequencies of these modes can be determined by perturbation theory, but the amplitudes of them are unknown, and that information has to come from numerical data. For each quasi-normal mode, we have both a prograde and a retrograde frequency. And essentially, if the perturbation, so if it is spinning, if the perturbation is in the same direction as the spin of the black hole, then it is a prograde frequency. And if the perturbation is in the opposite direction, then it is a retrograde frequency. Those will be two different frequencies. And for an aligned spin binary, you get everything, the perturbation will be in the same direction, largely, that the binary was initially spinning. So if the spin of the black hole, if the binary is going around like this, then the spin of the final black hole, it will also be spinning in that direction. If you have spins, so like in this bottom case, you have spins on both your black holes that are anti-parallel to the orbital angular momentum, so your black holes are spinning in a different direction to the direction of your binary, and they are large enough that when it merges, the difference between the two means that your perturbation is still opposite to the spin, then this is the situation in which you get a retrograde frequency. So mostly you only see retrograde frequencies. They all get excited, but you only see them dominate for high mass ratio systems with spins that are large enough that you get this effect. Yes?
So you need high mass ratio systems. Do you need any other orbital properties, like you need some eccentricity or precession to drive this anti-aligned configuration?
So this is fine
Okay.
for, aligned spin, quasi-circular, but yes, you need the high mass ratio.
Okay, but then your ring down is, well, relatively faint, I guess.
Yes.
I mean, I don't know how high you're talking. Is it
this
Q10,
is the theoretical
Q100?
picture.
Okay.
This is just setting the stage. The ring down frequency is important because when we build our model, like I was saying, the location of the dip in the phase derivative is given by the ring down frequency, for example.
Okay.
So when we input that is an analytic part of our model. We say, and we determine it. We have a point where we say this should be prograde. Oh, no, now we're negative. It's retrograde. And if we get that point wrong, then we get the waveform will be wrong, and we will have a section of our parameter space where we're very open to misestimating.
So do you have an idea of what mass ratios this effect becomes reasonable?
Where it starts to dominate?
Well, where retrograde modes can get excited. Let's put it that way.
It depends. There's a kind of line,
okay.
right? Like spin somewhere between, like maybe around as low as mass ratio 4, you might start to see them for very high spin systems. By mass ratio 8, you've definitely got a set for high spin. By mass ratio 18, now we have clear evidence and data. There's a kind of line across the Planck space. Okay. And negative spins, obviously. Okay, but remember what I was saying before about a processing system, which is that our perturbation is neither aligned nor anti-aligned with the direction of the final spin formed by the oscillation. And so we can have a perturbation, it will be at some sort of angle, might be in the upper hemisphere, might be in the lower hemisphere. And what we really need to know from our waveform modeling point of view is at what point is the prograde mode dominant and at what point is the retrograde mode dominant. And what we find is A, that both prograde and retrograde modes are excited for our systems, and B, largely it's It's this, if the aligned component is positive, then the prograde frequency will dominate, and if it's negative, then the retrograde frequency will dominate. However, because both of these are excited, we do have to take into account both of them. And so depending on this angle beta, we have some expression where we use both of the 2-1 and the 2-2. And this is again because, remember, when we're transforming into our coprocessing frame, in which we do all of our modeling, in this frame, we get the modes mix between the inertial frame perturbation theory, coprocessing frame model. So we now have to blend the two frequencies in the coprocessing frame so that when we rotate everything back into the inertial frame to get our final waveform, they separate out correctly. And yeah, this is quantified by this angle beta. So getting the model of the angles is not only essential for getting the sort of overall shape of the waveform, but it's actually fundamental to getting, the frequency and everything right. Yes.
No, this is probably just me getting confused, but so to get the frequencies from perturbation theory, you just need the remnant spin, right? And from there you get the frequencies of the quasi-normal modes. So
mass, yeah.
Right, but okay, but the mass one, okay.
Yeah.
But anyway, then so this dip in the frequency for processing waveforms, this dip occurs at which ring down frequency? Are we still interested in the fundamental QNM, like the 220? Is it?
No, it will occur at this shifted frequency because we're in the coprocessing frame.
Okay. No, I guess I'm just still confused. Like if you're thinking about the remnant mapping the coprocessing frame and the in-spiral or whatever, and then what's computed in the ring down, and then where the calibration is done. But it's probably just me.
I've probably skipped over this a bit. If we modeled the ring down in the perturbation theory inertial frame, we would not have, we would not see the dip because we would not have this nice smooth waveform. In the inertial frame, as a sketch, say, the phase derivative might look like this. When we transform into the inertial frame, we just get the nice simplified form. Sorry, into the coprocessing frame. We get the nice simplified form with a dip located at the ring down frequency. But this is no longer, the pure theory ring down frequency. This frequency is now sort of the convolution of the averaging, I don't know, mixing.
Okay, thanks.
Okay. Yes.
So when we say that a black hole depends only on mass and spin and like this QNM frequency characteristic of this is not entirely true because you need also to add this.
Can you say that again?
Yes.
I couldn't hear.
So when we say that QNM frequency characterizes fully the black hole, mass and spin, it's not exactly true then because you need to add also this angle between.
It characterizes the magnitude of the spin. It doesn't characterize the direction, I think. And your quasi-normal mode frequency only has two components, right? So it can only characterize two properties.
Yeah.
I guess maybe the point being that when you do perturbation theory, you have there's no sense of, you're just perturbing a curved black hole, right? So with whatever, and I don't know, there's just the one frame. I guess there's uncertainty in mapping that trying to take a full waveform or map with, if you're using the inference of the mass and spin from the in-spiral where there is precession, I think that's where the uncertainty is, right? But I don't know.
But the ring down waveform you observe, you can still describe as a superposition of these damped sinusoids. But as she's showing very clearly on the plot, you have multiple things and multiple modes will get excited. And so to get this, phonological waveform, you want to go back to the coprocessing frame where you can have a better interpretation through this weighted mixing. At least that's how I'm understanding the picture.
Yes. I don't know if it's quite the same question. One question maybe is, in perturbation theory, is not my area of expertise. But in perturbation theory, I have a perturbation which has a characteristic frequency, right? But I don't care what angle my perturbation is relative to my spin. And so the mass and the spin magnitude, they are determined by my frequency. I care what angle this is at because, yes, I'm trying to do a frame transformation. And so that's where this comes in. Okay. So then, to tie this all together, if we do everything correctly, if we capture every part of our waveform, then we get everything. So, for example, here we are, you can see that the model that does not correctly account for this effective ring down frequency, the shift in the frequency in the ring down, you get massive dephasing in the ring down. But when you do account for it in red, then you're able to capture the phasing correctly. Likewise, if you get this shape of beta through merger and ring down, that's what gets you the correct sort of envelope shape. So you've got the right sort of amplitude of your waveform going through merger and ring down. Whereas if you don't get it there, then you don't get the... here, basically, the model for beta hasn't done the drop. And so it's stayed too high. And so when it's stayed too high, it's still spreading out the power between all of the modes, when actually that power should now be being funneled much more into the 2-2, into the dominant mode, and so you get more power in the waveform. And similarly, during the in-spiral stage, you want the most accurate. Well, okay, this has been aligned, so if you get the phasing wrong here, you will also get the phasing wrong here. But if you use the most accurate PN prescription available, then you will get the most accurate prescription. You will get the least dephasing in your waveform, and you will get the correct amplitude of your gravitational wave. Okay, and again, we bring this back to the match. So this is a case where the waveforms have a much higher match, and you can see that clearly represented here, and they have a much worse match. So you can imagine that the blue waveform, you might well mischaracterize your source when you get, if you're using this model, whereas you hope that for the red waveform you don't. But the degree to which you mischaracterize your source, you don't know, because you'll only mischaracterize it if this waveform is not the closest possible waveform, right? If for the blue model, it's still the best possible match, then you will still get the right parameters. It's only if somehow you're getting a confusion that you're going to start to see bias in your waveform.
Yeah.
Yes?
The problem is then if you want to do tests of general relativity and you allow parameters to float, then this becomes concerning.
Yeah. Definitely this kind of model error might incorrectly imply violations of GR, but it might not necessarily give you the wrong source parameters. Okay, so very quickly, in the remaining time, an overview of the models available to us. Again, it's just a long list of models, but you can see that they're separated out into the different approaches that we talked about at the beginning, the surrogate models, the NR surrogate models, the phenom models, and the EOB models. And this, again, is time domain, frequency domain, time domain, time domain. So, okay, as talked about at the beginning, disadvantage of the NR surrogate approach, no complete in-spiral, but this is here everywhere. Also limited parameter space. But you do get calibration to every feature that is included in your model. So that's all there. So therefore, it will be the most accurate model. And other models, you can still have a processing model, for example, where you haven't involved all the components of calibration to NR. You just use the PN and extend it through, and it normally doesn't do something crazy, so you can get a rough description. Yes.
So I think I remember that when Phenom X family, the waveforms were first surviving, there were only a handful of numerical relativity waveforms that had mass ratio up to 8 or something, and significant spins. Now, I know now as of May or whatever, the SXS catalog is much bigger. You have high mass ratios. are these all calibrated to the new ones as well, or like the Phenom and the EOB Cam? Is that under plan? Okay.
Underway.
Underway.
Even, so the surrogate model, it takes ages
Sure.
to bring out the next one. But even for the semi-analytic models, it's a very long process to extend the calibration. So yes, it's underway, but will take time. And the models that I've listed here are all, fully publicly available. Most have undergone review and testing to make sure, we have a proper assessment of their model accuracy. So it's normally at least a 2-year turnaround time
2 years, okay.
for some sort of minor model development.
Thanks.
Yes?
Thanks. Yeah, I'm looking at the calibration. I mean, for the processing sector, it's kind of cross, but the Phenom GPHM is supposed to be processing, so.
So it's processing, but it uses, it extends the PN results through merger, and then connects them to black hole perturbation theory results in the ring down.
So without the NR calibration.
So yeah, and that's the same for all the models here where we don't have a calibration to NR. But some models, for example, the V5 PHM model, they are able to include various features that have come from the calibration. So they include the effective ring down frequency. They capture that correctly. It doesn't require calibration to NR in order to do that. You can do that with your own model of the angles. And so they have better accuracy in that section over Phenom T, for example, without NR calibration. Okay. One of the biggest challenges when building up all these models is producing the higher order modes. And this is partly because when we come to calibrating things, you can see that for our NR waveforms, these are just an example, but at a mass ratio 1 system, our higher order modes are just lost in the noise of the data. And so it's extremely difficult to produce an accurate model. Okay, at Q8, fine, we start to see them. But then, you could be asking, but there are even higher modes here that are making this kind of contribution that aren't even output by our simulation. So that's the problem. So when we create the models, the higher modes are one of the limiting factors in the accuracy of the model. And you can see particularly that the dominant multipole tends to have a match that is up to an order of magnitude better than the higher order multipoles. I think that is supported. I can't see that. Okay. And then we want to say, when we look at our overall models, how well do these models perform in comparison to each other? So this is just a comparison of the semi-analytic models. You can imagine that if the surrogate plot is here, it would be sort of out here as an order of magnitude better. And we can see that in general, actually, all our models at the moment are roughly comparable, except for the surrogate. Okay, the EOB model is maybe better by a factor of up to 2, but really factors of 2 don't mean that much when we're talking about how accurate is my model across the parameter space. But as before, we now want to relate these sorts of histograms to our mismatch criterion, which will depend on the SNR and all sorts of things. For most cases, the mismatch criterion for the sort of thing that we're dealing with LIGO sources is likely to be out here, and 90% of our distribution, they are all below the threshold that we need. They are good enough for what we're using them for. For very extreme regions of the parameter space or for very loud signals, this may not be true, and in fact, we have recently seen challenging events. For LISA, not one of these models will be good enough. So, somehow that's got to change. But even, yesterday I was talking about how accurate your NR is, and even the NR for some cases might be pushing the threshold of what we need for LISA. So the foundation on which we build our models has got to be improved in order to improve the models further. And
What's the NR accuracy?
what limits the NR. I mean, partly resolution, for example, if you ran higher resolution, more computationally efficient simulations, it would be better, but also the numerical techniques employed for finite differencing codes, for example, you might need higher finite differencing implemented, or just an entirely new approach. It depends how far off the NR codes actually are, and there is disagreement. And as I was talking about, disagreement about how to even estimate this, and then disagreement about what the threshold actually is, and so we'll see. Also the extraction. That challenge is being met, I would say, with the techniques like the Cauchy characteristic extraction and the possible hyperpoloidal slicing. I can believe that in 5 years' time, say that error is not a main source anymore. Things like resolution, I have less faith. Okay. And then the other, this is relating it back. This is just an example. This is typical. This is what we see. This is for a case where we're well within, the bulk of the distribution. Everything's fine. It's a reasonable. It's not an insignificant binary. It has, I think, mass ratio 4, a processing spin of magnitude 0.6. We're still, pretty much all models doing very well here. We're accurately recovering the parameter. If we raise the spins, maybe we have a high inclination, so we're really seeing these higher order modes, which are really challenging to model, and we're now at a point where all our processing systems are breaking down, then we really do encounter regions of the parameter space where some of our models might be correct, some of our models are not correct. Which model is correct or not depends where you are in parameter space. It's not, it's not, annoyingly, it would be so nice to say, okay, this model is always correct. Okay, the surrogate is usually correct, but restricted to where in parameter space you can employ it. And I should note that here, the injection is with the surrogate, so it really should be correct. But you can do the same sort of thing with NR, and you'll see the same sort of pattern. And we have here 2 models where the correct value is outside the 90% confidence entirely. So yeah, but we are outside the NR calibration region for these cases. And then also the one other thing we need to consider, which I haven't really talked about so much, but is this computational efficiency. And again, loosely we see the sort of thing that I've talked about already, where the phenom models are maybe an order of magnitude more efficient than the effective one-body models. As you include more physics, so this blue line, for example, the blue line and the red line, they include a more accurate in-spiral description of the precession angles and are slower than the one that just includes the closed form expression. And so you are always balancing, do I want the most accurate description I can have, or am I okay in this region to use something that's less expensive? And again, for LISA, where you'll have these super long signals, we will have to find ways that during the in-spiral where the closed form expressions are more accurate, we can sort of stitch those on together. Okay, I have one last slide. And then I just wanted, because largely in this talk I have talked about quasi-circular processing models, I just wanted to give a very quick overview of the fact that eccentric models are out there. They are coming. Largely, so there are some surrogate models sort of being produced so far. The semi-analytic models don't have any calibration to numerical relativity. The surrogate models don't have any spin at all. None of them have precession included. We need to be able to go in and put all of these components together to have fully generic models describing everything. Thank you.
questions, but maybe if somebody has one urgent, pressing question. There's the time. I think there's.
We're done. Yes.
Okay, let's